We're moving on to the last section in chapter 2, bell-shaped data. We're going to do an overlap on mean and standard deviation, which is number 5. And then we're going to, oops, someone just appeared. And then we're going to look at what's called the 68, 95, 99% rule. We're going to use standard deviation and mean and things to look at outliers. We're then going to look at z-scores. So we've got a whole load of cool things to learn about today. Let's go and look at means and standard deviations again. Okay, let's do this. I'm going to collect data from you only if you wish to share. And simply, all you're going to do is tell me your age, if you want to do that. So I'm putting in my age, and just call it out, and I'll try and catch 6 or so numbers.
59.
26.
I almost made myself too young. I'm 66. 26. Okay.
17.
17. Couple more.
38.
16.
38. And who said after 38?
16.
16. Okay, we got enough. Right. So just looking at this raw data, would you agree that this data is all over the place, right? It's very spread out. And let's just pretend for argument's sake that I did it with a huge class. You would still see that kind of variation when you did, you know, because these people are still in the class, right? So you know it's all over the place. So I would expect to see a pretty decent size standard deviation, right? And I'm also going to calculate the mean, but we're going to use this so that we can let the calculator do it for us, because I think it just makes life easier in the long term. So you hit the start button, choice number 1 is edit, and then delete the old data from whatever the last question you did was, and go 66, 59, 26, 17, 38, and 16. So that's not hard, right? Type in the data.
Can
Once
I
you've
get
got,
you to, can I get you to do the start thing again? I didn't have my calculator in my hand.
sure, I can
And-
do it again. Right, so you
Okay.
hit the start button first.
The,
Right, S,
the what? The stat button? Oh, stat
Yes.
button. Okay.
right, hit that
Right.
first.
Okay.
Right, and
So I need
you
to turn
see,
it on first?
then hit number 1, edit.
Okay.
type in
Okay.
your
I see that.
numbers.
Yep.
Okay, got those guys?
How do I? Oh, number 1. Okay. Got it. Yep. I see it now.
Right, you got the, you typed in your numbers, the 66 and all that good stuff.
Okay. So, yeah, I do that. Enter. Enter.
Okay.
38. Yep, got it.
So what you've done, what you do after that is you hit the start button again.
Stat button.
And this time you're going to move from the edit to the calc menu. So right now it's highlighted as edit, and I'm going to move it across one to the calc menu. And you do that by hitting this button here.
I hit what button? Oh, okay.
This button here. Right?
Yeah, got it.
Now it's exactly where I want it to be. It's on one variable statistic. So you hit enter,
Okay.
and you'll see something that looks like that. Some of you get a
Variable
slightly different version, right? And you then do the blue button. In my case, it's a blue button. Some are yellow or orange, right? That
Second.
color button, second button, and number
Okay.
1. And what you're telling the calculator is get the data from that column that my data was in, which was
Okay.
L1. Now, when I hit enter, the guys that we are interested in are the mean, which uses that symbol. And the mean, by sheer luck, is a nice number, 37. And then the standard deviation is this guy here, the one that says 21.39 and all that stuff. You see that one there?
Then-
It looks like that on the calculator.
Mhm.
And
Yeah, I
so
see it.
that's the guy that represents the standard deviation. And I'm going to just round him off to 1 decimal place.
Yeah, just 37. Okay. 37. I don't know.
Okay. Now, you know that this video will be online and you can go and, pause it and rewind it and pause it again and go through the steps. But that's essentially the steps that we're going to use. So what I'm going to do now is take this mean and standard deviation and play about with it a little bit. First thing we're going to do is we're going to create an interval where all the good numbers live and the outliers live outside it. So the test for an outlier is that you calculate the interval that's made by the mean plus or minus 3 standard deviations. So in this case, 37 plus or minus 3 lots of 21.4. So that's going to be 37 plus or minus 63, oops, can't count, 64.2. Now, if you add these two together, you get 101.2. And if you subtract one from the other, do you notice that you would end up with a negative number? So this is when context comes in. If you know that the numbers that you're dealing with are ages, would you agree that the youngest age is somebody brought in a baby that was just born? So 0 is the youngest age you would expect. Even although 37 take away 64 is 0, is beyond 0. We only do 0. So can you see that based on this very small data set, wouldn't you have to be really, really old before you would be considered an outlier? And if you think about it, if there's only 6 numbers and the biggest one is 66, could you imagine it wouldn't be impossible that you could have other people if you went and asked further on. So the test for being an outlier is that you're outside this range. So if you're outside this interval, you are an outlier. Now, I used this data so that we could just get practice at doing the calculator. So I want you to imagine that I got some more data on a different class, maybe with lots of students in it, and the average age was 23, and that the standard deviation was 10. So let's find out what numbers are outliers. So the test is you find this interval. If you take the mean, it's 23, add or subtract 3 lots of 10. So that's what, 23, add or subtract 30. If you add 30 to this, you get 53. What would you get if you take 30 away from 23?
-7.
And because this is ages, won't we use common
0.
sense approach and we'll finish at 0? So what this is saying for this class, don't you have to be older than 53? 53, you just make it. Don't you have to be older than 53 to be considered an outlier? So for instance, Rob, you're an outlier in this class. So if you went to this class, you would be the old guy. Well, actually, so would I be, right? We would be the old guys. Why? Because our ages are bigger than 53. Now, same data, but instead of being ages, which is what it was the first time, I want you to imagine that this was the temperature of some place, right? And probably in centigrade. Well, same calculation all the way down to here. But now context kicks in. If you take 23 and subtract it, doesn't -7 now make sense in the context of temperatures? Couldn't you get -7 Fahrenheit or -7 centigrade, whatever was the measurements? So if you were collecting data on the temperatures in a place for a whole year, wouldn't this represent the normal typical range? and it would be an exceptionally cold day if it was less than -7, and an exceptionally warm day if it was bigger than 53 centigrade. Does that make sense, that we now have a way of deciding who outliers are by using this test? If you're more or less than 3 standard deviations away from the mean, you're an outlier. Any questions about that, or do you feel comfortable with what we've just did? We feel good. Okay.
Oh, I have a
Yes.
question.
Yes,
Maybe
James.
I missed something, but when we did the equation on the previous page, the mean was 37 and now it is 23.
Yeah. I made a new question with new data.
Oh, okay. All right. My bad.
That's all that is. This one we did with the class, and this was fine, but I wanted another one that we could just say, we've already done it, but with different data set, different numbers. Now, suppose I had a data set that looked like this. In fact, this is question 1B. I could, put it into the calculator and get the answer, and I would get the right answer. But this is a special case. I know the answer to what the mean and standard deviation of this rather weird data set is. What's the mean of this data?
24?
Yeah. Would you agree if all the numbers are 24, the average is 24, right? The mean's 24. Maybe less obvious, but what's the standard deviation of this data? Remember, standard deviation is a number that tells you how spread out things are, right? Whether they're all over the place or they're quite close to each other.
0.
0?
Yes. Now, can you trust me, if you put it into the calculator, you get 0. So can you see that you might be able to make an intelligent assumption on some data sets, whether or not one, what the values are. But not a very common thing, but it's kind of cool. How about this data set? Let's just say, for argument's sake, that I calculated the standard deviation of this data set. And I'm making this number up, but let's pretend it was 3.1. What's the standard deviation of this data set without going near a calculator?
31? No.
3.1. Why is it the same number, even though these are a lot bigger than that?
The interval between the numbers are still the same.
Aren't they spread out the same amount in both cases?
Yeah.
Right. It's a bit like you took some numbers here and you shifted them over here. But aren't they still as spread out as they were before? So what that tells us is that standard deviation, right, the number that is the standard deviation, doesn't care what the values are. It doesn't care that they're 30s or 10s or any other number. Doesn't it only care how spread out they are compared to the other numbers that are near it? On the other hand, if I did the mean of this guy, you just have to trust me on this one. The mean of this guy is 5 and the mean of this guy would be 35. Do you see that the mean does care what the numbers are, right? It's quite clear that the mean of that second data set is a much bigger number than the mean of the first data set. But the standard deviations remain the same, which might, I think, is interesting. Right, are we okay with the following? If I gave you a set of data Are you comfortable that you could plug it into your calculator and get the standard deviation in the mean? Right?
Maybe.
Right. Well, hopefully after a few questions, you'll get up to speed on it, right? And secondly,
609
yes, Rob?
696 pages to the manual for this thing. This calculator has more pages of instructions than my computer does.
Yeah, you don't, 99% of them you'll never look at, so I don't think you need to worry. Yeah, I mean, it could be overwhelming if you look at a book and you think, oh God, do I have to read this thing? Probably not. The only bits you need to read are when you come across, I wanted to do this. Okay, I'll look up the bit of the, the instruction thing that tells me. So if I give you a set of data, you can use the calculator to get the mean and standard deviation, hopefully. Could you also find that interval where the outliers live, right? The mean plus or minus 3 standard deviations. And so if I gave you a set of data and then I said, is 82 years an outlier or not? You could calculate it. Is a 4-year-old an outlier or not? You could calculate it. Right? That's kind of what we've done so far. So the next thing that we're going to look at is number 6. And can you imagine that we had some data that was symmetric? Now, life is never perfect, but roughly we'll do. Can you imagine we got some data that's roughly symmetric, like this one is, right? And we call this shape, well, we have a couple of names for it. The most common names we use is we say it's symmetric. But you'll also see it called bell-shaped. Now, it doesn't mean it's a different thing. I mean, they're the same thing, right? Bell-shape's not a bad name. I mean, doesn't it look a bit like a bell, an old-fashioned bell, side on? So it's not a bad name. Now, if you calculate the mean, it probably doesn't surprise you, shouldn't really, that the mean would be right in the middle where the hill is, right? So whatever this number is, that would be the median, right? The mean, I should say as well, right? Right in the middle. What they've discovered is even more surprising than that. That if you have symmetric data and you calculate just 2 numbers, that's the only numerical summaries that you're going to use. And the 2 numbers that you need are called the mean and the standard deviation. That you can actually draw a pretty accurate shape of what all the data was. So maybe you got, and let's take an example. You got 2,000 people, right? You got a sampling, 2,000 people. That's a lot of people. And you found out that their mean IQ was 100 and that the standard deviation was, say, 10. Right in the center is going to be the most common IQ, would be 100, right? More people will have an IQ of 100 than any other IQ out that 2,000 people. That's not too big a surprise. What they discovered is something that is a surprise. If you take the mean and you add and subtract 1 standard deviation, so you add and subtract 10 from the mean of 100, right? So you get to 90 and 110. So you get to here and you get to here. The number of people, the percentage of all your data in that range is 68%. And that is a kind of truism. It doesn't matter if you're collecting data about people's height, weight, IQ, how many minutes it takes them to walk to the shops, or whatever the data happens to be. If it is a nice symmetric data within 1 standard deviation of the mean, we've discovered that approximately 68% of all the people. So in my story, 68% of people, Americans, have an IQ in the range 90 to 110. And then they take it a bit further. If you start at the mean, but you add 2 and subtract 2 standard deviations, so you go to 120 and 80, right? So you go to here and you go to here. Then in this range, right, from 80 to 120, 95% of all the data lies in that range. Isn't that remarkable that that property has been found to be true? That if you take just the mean and add 2 standard deviations and subtract 2 standard deviations, you get 95% of all the people in that range. So 95% of Americans have an IQ somewhere between 80 to 120. And then you do it one last time. And I'm running short of colors, so what am I going for? I'm going to go for black. If you start with the mean and you add 3 standard deviations, or you subtract 3 standard deviations, you get to here. And since my picture is getting pretty messy, between 70 and 130, right? IQs between 70 and 130, a rather weird number, 99.7% of all the data lies. Now, this rule, this property that I've just kind of tried to describe on this rather detailed diagram, there's a lot going on in it, has a name. This property is called the 68, 95, 99.7 rule, which is a pretty long name for something, but isn't it a good name because it helps you to remember where all the numbers go, right? It's a 68, 95, 99.7 rule. Okay. So imagine that I collected some data on the height of Scotsmen. And I found out that their average height was 66 inches and that their standard deviation was 5 inches. And we knew, because we did a histogram or whatever, that the data was approximately normal, right? Approximately symmetric. I can use just these 2 numbers to build up one of these ones, and we can get a range of values. So you draw this guy, you draw a hill, right in the middle, you put them in. And then you go 1, 2, 3 little check marks, 1, 2, 3 little check marks. And you add 1 standard deviation. Then you add 1 more standard deviation. Then you add 1 more. Do you see how I got those numbers? Add 5, add 5, add 5. Now, if you go backwards, take away 5, take away 5, take away 5. And at each of these points, there's a kind of little vertical line, just a way of keeping track of things. So for instance, if I take this guy here and I go just 1 standard deviation either side, can't I say that 68% of adult males are in the range 61 to 71 inches? Do you get a feel for how many, what the kind of height of a Scotsman is? Somewhere between, most of them are somewhere between 5 and 6 feet, right? They're not 6 feet and they're not 5 feet, but they're in that range, 5 to 6 feet. And then you could do 95%. But if I wanted to find out what range 95%, what would be my start and finish number that I would use?
56 and 76.
Right, so you would go 2 standard deviations from the mean. So that would be 56 to 76. So wouldn't that pretty much be almost all Scotsmen, right? 95% of them, not everyone, of course. If you went all the way to the extreme, which is 3 standard deviations, you would get 51 inches to 81 inches. Do you notice that this diagram doesn't include everybody? Because isn't 99.7 not 100%? That's not everyone. It's darn close to everyone, agreed? But it's not everyone. So what about the rest, the 0.3% that's left over? Well, don't the 0.3% live down here and down here? Right, 0.3%, right? Everybody else who's left is left in these little tails. Now they're tiny, which if you 0.3% is not a lot of people, but you know, in a population of millions, it still adds up, right? Who are these people? Well, it depends on the storyline. In this question here, wouldn't you probably call these the people who are geniuses, right? High, extra high IQs, right? The kind of Einstein people, right? And the ones down here are football players. Oh, come on. Did you get that one, football players?
Easy, not until they've been hit in the head a few times anyway.
Right. That was me just getting a dig at football players. In the Scottish case then, wouldn't people who are over 81 inches be, you know, really rare? You wouldn't meet many people in America over 81 inches either, right? But, you know, we're talking massively tall people, right? People that if you saw them in the street, you would probably give them a second look, which you shouldn't, but you know, sometimes that's just what happens when you see something you're not expecting. So we now have a very good way of only knowing 2 numbers and the fact that it's roughly symmetric. We now have a way of getting a bigger picture of what the data looks like. Remember my 3 standard deviation rule? You have to be outside it to be an outlier. Isn't my 3 standard deviation rule all these people? So bigger than 81 and less than 51. Isn't that the same 3 standard deviations away from the mean? You see there's a little overlap there. So the people who live at the extreme ends, isn't that where the outlier should live, right? Extremely unusually big, extremely unusually small. Any questions about that? Are we good? Right, let me show you what the homework questions look like, because they're not that different from what I've just done. I'll talk through one once I get this damn thing to pay attention to me. There we go. Let's show you what that guy looks like. So in this question here, can you see you're just going to use your calculator or your common sense to decide what the mean and standard deviation? You remember that one, 24 and 0, right? But you could do any of these and all of these with the calculator, right? Here's one of my distribution ones. This one here is about students and sleeping. And they want to know a 68, a 95, or a 99.7. So that's going to be, you know, the ranges that I just did with the IQs and the Scottish people's height. Yes.
Have you shared your screen? Because all I'm seeing is your video.
You see it now?
Yes.
Okay, so say that back again. In question 1, calculator mean and standard deviation. Unless you recognize that one as being a special case that you can do without it. In this question, it's the 68, 95, 99.7, right? That's the kind of IQ questions and the Scotsman's height questions. This one here, same idea. So let's do a version of 3. In question 3, you're looking at 4-year-old kids, and they did a big sample of 4-year-old kids, and they found out that their average heartbeat is 107, and that the standard deviation for these kids are 6 beats per minute. And then they say, use the empirical rule. The empirical rule is another name for the name I prefer, the 68, 95, 99.7% rule. Would you agree that rule is much better name than just calling it the empirical rule? Because if you call it the empirical rule, you might forget what else it's about, right? But at least if you put a name on it. So in that question, we are going to find out the range of 4-year-old kids' heartbeats, which probably explains why 4-year-olds run about like they're on gasoline, right? If their heart is going that fast, they're probably pumping blood all over the place and running and energetic and all sorts of cool stuff, right? So I like doing it visually, although you don't need it for this question. So there is all the 4-year-olds, and right in the middle is 107, right? That's my X-bar. 1 standard deviation, 2 standard deviations, 3 standard deviations. Are you happy how I added 6, and added 6? Now, if you go the other side, take away 6, take away 6, and finally take away 6. Right, so if you want to know what range of heartbeats are 68% of the kids, it's all the kids between here and here. So 101 to 113. If you want to know the 95%, it's between here and here. And for 95% then, it's going to be heartbeats between 95 all the way up to 119. And for 99.7, it's here to here. Are you comfortable about how this data produces this picture, which then gives us these intervals? Do you feel comfortable about how we do the process? Right. Now, I'm making this up, but imagine that you're a doctor, you know, one that does deals with children, and your 4-year-old goes in for a checkup, right? Once a year or something, you get a checkup to make sure everything's going. And he gets his heartbeat, and he finds out that this kid's heartbeat is 140. Why should the doctor be worried?
It's in the outlier.
It's an outlier. And aren't 140, it's over here somewhere, right? Isn't this where unusual things are happening? Wouldn't that be an unusually high heartbeat for a kid? Now, maybe it's just a reflection on the kid's extra energetic and they had 5 ice creams before he came, which case none to worry about. But couldn't it also be a heart issue that they may want to spend a little bit more time looking into? And the same argument would be if the child's heartbeat was 80, which might be quite good for an adult, but not very good for a kid who's 4 years old, because wouldn't an 80 be a way over here in the outliers? That would be an extremely low heartbeat for a 4-year-old. So can you see if doctors have data like this, can't they then decide what is unusual for a particular group of people, right? Because won't a 10-year-old child probably be different than a 4-year-old child, right? Because as you develop, your body gets bigger and, you know, things change. And so having this data allows them to be able to, when they check the child's heart rate and, you know, all the other things, their weights, their height, that they can look at that child and say, yep, your child is growing exactly the way a 4-year-old should be, right? They're in that middle range for height and weight and their heartbeat and all the other good stuff. And you get like a clean bill of health and you're good. But if anything is a little bit untowards, right, especially in these extremes, isn't that an indication that maybe they might want to look into it and see what's going on? So this is useful, isn't it? Imagine if you're in a nursing, data like this is helpful. And you might say, well, where did they get all this data? Well, you know, don't they have thousands of kids getting their heart rate who are 4 years old all the time? All they do is they collect all that data, right? Without names, they don't need names. And they stick it in the pool, and the government collects data for all sorts of things, medical data included for hospitals, for instance, do that. And it's so that everybody can benefit from that knowledge. I like that. I like that stuff. It's good. Now I'm going to try and return back to the homework, and we'll look at some more homework questions. Would you agree question 4 is just use your calculator with some data and get means and standard deviations, right? Pretty, you know, hit buttons and you're good to go. Oh, and I didn't realize that was the end of that. Let me check. Okay, skip those questions. Let's go to 7. Here is your data set, all these red numbers. Won't you be able to get the mean and standard deviation of those two guys? There is a new guy in town. He's called the variance. And they even tell you its name. The variance is called S squared. Right. Let's just pretend that I calculated the standard deviation and it was 8, just for argument's sake. What do you think the variance is equal to? Even although I've not talked about it.
64.
Based on its, yeah. Do you see why S squared is probably quite a good name for a variance? Yeah, a good label. And it would be 8 squared, it would be 64. I'll leave them. And that's about standard deviation and mean and the empirical rule kind of covered. So what's left? Not a lot of questions, but quite a good idea, quite an important idea. I want to give you a story to show you what this thing's about. We are going to look at what's called Z-scores, or to give them their full title, standard, I should start again, standardized Z-scores. Nobody uses the full title. We all call them Z-scores, right? But their full title is standardized Z-scores, which is fine. So let me give you a story and then we'll come back to these guys because the story is going to be directly related to things called Z-scores. And the story is, how do you fairly compare two different test scores? So here's my story. There are 2 twin girls, and one of them is called Mary. I'm going to call her A for short. And her twin sister is called June. And they go to their high school, and they both go to a different English class. And they get a final exam. And in that final exam, right, the mean of Mary's class, class A, the mean in that exam was 75, and the standard deviation in that exam was 10. In June, she was in a class, and the mean in her class was 50, and the standard deviation in her class was 5. And Mary and June, this is what Mary got. She went and got 83. And June, she got 73. And when they got home, they were arguing about who did best. And Mary went and said, Well, I got 83 and you only got 73. So obviously I did better because I got a higher score. And then June said, yeah, but your test was different than mine. You got a dead easy test. I got a really difficult test. And you can tell I got a difficult test. Isn't the average in her class a lot lower than the average in our class? And she says, my score is 73. It's much harder to get in this class than you getting an 83 in that class. I bet you if you came to my class, you wouldn't get 83. I bet if you were in my class, you wouldn't even get 73. That's because I'm better at English than you are. You know how sisters fight, right? What we got to do is figure out, is there a fair way to compare two sets of data where the data are not the same, right? Different means different standard deviations. Right? Can you see that that's an issue that you want to be able to agree with? I know I haven't done this, but I'm going to try it. It might work. I'm putting you on pictures. Do you know that you can put little thumbs up things, right? You know, the little one. If you're wondering where it is, it's inside reactions. And you can do things like a little check mark, or you can do a little cross mark, or when you hear one of my jokes, it's that funny you can cry. You see those? Oh, you like those. Right. There are two people, Mary who's A and June who's B. Okay. Now, Mary was the one that got 83 in the easy test, and June was the one who got 73 in the hard test, right? Gut feeling, no other thing. I want you to put a check mark if you think it's Mary, and a cross mark if you think it was June. So a little check mark if you think it was Mary, a little cross mark if you can think it was June, and we'll do a kind of quick summary. It looks like, for those who are taking part here, would you agree that the cross marks have won? In other words, most of you think it's going to be June, right? She got 73 in the hard test. Good news is you're right. So your gut feeling was correct. What made you think that before we show you how to prove that that's actually true?
She's an outlier in that particular class.
She is. Isn't she a really big outlier? I mean, if you do the 3 standard deviations. Well, some of you just saying, look, in a class that's got 50 and a very small standard deviation, isn't it really hard to get a big score like 73? Right. So what is this Z-score? How's that going to help us? This is the formula for getting a Z-score. In English, it's data, take away the mean, divided by the standard deviation. I'll do ST for sure. So, right, so I'm going to do a Z-score for Mary and a Z-score for June. Whoever gets the biggest Z-score, they were the person who did best, right? Big is best in this context, right? So let's do Mary first. Mary's Z-score. Well, she got data, so her data is 83. That's what she got. You take away 75 and you divide it by 10, and I'll put that answer in a minute. And next door, we're going to compare her twin sister, June. And in June's case, she got 73, take away 50, and you're going to divide it by 5. And I'm going to show you a little thing that you have to be careful of. I'm going to do this calculation wrongly, right? So I'm going to just kick out before I do this. I'm going to make you mute. So if you want to talk, just hit the space bar. We're back again. So I'm going to show you this calculation here. I'm going to do it wrong. 83, take away 75, divided by 10. That's the wrong answer. It's not the correct answer. What do I need to do to get the right answer?
You can either put brackets around the 75 divided by, or the difference, the 83 minus 75, then divide by 10.
You remember that thing, order of operations. Don't you want to subtract the 2 at the top before you finally divide? So if you want to do it, that bracket thing, what do you call them Americans, parenthesis, you get 0.8. Now, if I do June, I'm convinced she's going to be bigger. So 73, take away 50, and then divide by 5. And the answer we get is 4.6. Do you see that it's not even a close run thing? Didn't June do a lot better than Mary based on the difficulty of the class and how spread out they are? Does that seem like a reasonably good way, a fair way of comparing 2 sets of data when the populations, right, are quite different as they are here? Are we good? Do you like that one? Right. Let's give you one to try. I have a brother. I have lots of brothers. Well, I have a few brothers. This is me. This is my brother, David. He's just a couple of years younger than me. And the mean in my class was 75. And the standard deviation in my class was 10. And I got 83. And my brother David, he got a class through 70. And the standard deviation was 12. And he also got 83. Who did best? Use Z-scores to find out. Me or my brother David? And you've got no rush.
David, but not by much.
Sounds about right. Is that gut feeling or you've done the number crunching?
Done the numbers.
Yeah. Got 30 more seconds for the rest of you to catch up, because that's basically us finished for today. When you looked at the data, was it kind of hard to decide? Or did some of you think it was more likely to be David because the average was lower? Let's find out. It's going to be data, take away the mean, divided by 10. So I believe that is 0.8. And that's actually me, so that's done. And then if we do this one, I'll do that in the calculator because I don't trust my ability. It's 1 point something, I believe.
1.08.
1.08. Would you agree that in this case, just as you said, someone said earlier, that David actually did better than I did? But it's damn close. You agree there's not an awful lot between the Z-scores, right? Suppose the Z-scores were equal. Suppose both Z-scores were 0.8, for instance. What would that mean?
Tie.
It's a tie. Right.